everyone, I am G.H. Hardy.
And I am Weinberg, and we are here to show you this helpful equation we made to measure allelic frequencies in the population.
Allelic frequencies are the percentages of homozygous recessive individuals, heterozygous individuals, and homozygous dominant individuals in a population.
Let's start by going over the factors that put a population in equilibrium, or as we like to call it, Hardy-Weinberg equilibrium.
There are 5 factors that put a population in Hardy-Weinberg equilibrium. Number 1 is no net mutations occurring. Number 2 is no natural selection. Number 3 is a large population size. Number 4 is random mating. And number 5 is no gene flow. This means that no organisms are moving into or out of the population. Now let's break down the equation. Here's our equation that calculates allelic frequency shifts in a population. We have p squared plus 2pq plus q squared equals 1, or the related equation, 1 equals p plus q.
So what do all these terms mean? Well, P represents the frequency of the dominant allele. Q represents the frequency of the recessive allele. P squared represents the percentage of the dominant individuals. Q squared represents the percentage of recessive individuals. There's one more. Don't forget about 2pq, which represents the percentage of heterozygous individuals in the population.
So you have 360 brown cats.
And say you have 640 orange cats.
So, here's our problem. Find the percentage of heterozygous individuals, big F, little f, in the cat population if the allele for orange fur, big F, is dominant over the allele for brown fur, little f. We have 360 brown cats and 640 orange cats. Step 1 is to determine the total population size and the value of q squared, or the percentage of homozygous recessive individuals in the population. First, I took the 360 brown cats and added to the 640 orange cats to get the total number of cats in the population, which is 1,000 cats. Then, to find the q squared value, I took the recessive individual number, which is the 360 from the brown cats, and divided it by 1,000, which is the total number of individuals in the population. And when you do that, you're going to get 0.36, which is going to be your q squared value.
Our next objective is to find Q by using Q squared. Here we use the Q squared value that we determined from the last step, which is 0.36. We find Q by taking the square root of 0.36. This would mean that our Q value, the frequency of the homozygous recessive allele, is equal to 0.6.
In step 3, we'll use one of our original equations, p plus q equals 1, to find the value of p. First, we substituted the q value that we got in the last step, 0.6, into the equation, so that you would get p plus 0.6 equals 1. Then, using skills learned in Algebra 1, we would subtract 0.6 from both sides, and we would get p is equal to 0.4.
In step 4, we use p squared plus 2pq plus q squared equals 1 to find the percentage of heterozygous individuals, which was our original objective. So what do we know? From the past steps, we determined that p is equal to 0.4 and q is equal to 0.6. Since 2pq is the percentage of heterozygous individuals, we plug in the p and q values. From that, we determined that 2pq is equal to 0.48. This means that the answer to this problem is that 48% of heterozygous individuals are part of the cat population.
In the fifth and final step of this process, we checked our answer by plugging in all values, and it checks out.
So that just about wraps up this segment of learning Hardy-Weinberg, equilibrium, and the equation.
Now you know 2 things. 1, how to utilize the equations and what they mean, and 2, you know that we look stunning in black and white. Thank you. We'll see you next time. Oh, I almost forgot.
Don't forget to mind your P's and Q's.